in theory still on time, 3:30. In theory. All right. We have about, I think, 6 lectures or 7 lectures left, including today. And I don't know, we are sort of running out of time because there's lots of topics. With a naive attitude, I thought we would have time to cover, and I realized it's not going to happen. So hopefully I don't disappoint you, and hopefully there is going to be some learning in the projects if we're going to have project presentations, because as of today I still don't have a room. Okay, and I don't think we will actually get a room beyond my basement. But the presentations are going to happen, they're going to be videotaped. So don't complain in November, sorry, we cannot locate you, professor, you know, when are you coming back from China? If you have questions about your project, now you ask, okay? Complaints, you keep them for January. Okay, so I want to be sure that everybody works on their project. Now I'm going to tell you some good news that I got about a minute ago before I came to this room. Except my students, does anybody knows what this sign means? I mean, it's just it's calligraphics basically, but can be a subliminal message of some weird organization. So nobody knows anything? Okay. So anyways, as I think I had mentioned, part of the course, the course was basically part of a master plan to integrate computational science with statistics and machine learning. And so the university officially, I believe as of last Friday, they established this center. Not quite sure what that means in detail, but there is now an official certification from the provost that this is a university center, and so the details is to be found soon. But certainly what I anticipate is that we're going to have more courses like this one. We will be able to hire, I hope, in the future, more people that are willing to teach challenging courses rather than courses overlapping with each other, doing the same thing all the time. And more importantly, for those who are interested to do a PhD in this area, and I suppose lots of you doesn't include them, we hope to be able to offer directly PhDs. That's the plan from this center, so you don't even have to be directly affiliated with a department. Now, of course, I realize, and I'm on tape now, that you know, some departments may mistakenly think that this is a competition, but what we think is going to be an instrument that attracts students that otherwise are not going to go to mechanical or electrical or computer science, right? So we need the students who basically are looking for something different. All right, so we have 4 homeworks. There's going to be a 5th homework tonight, and I think it's almost certain there's going to be a 6th homework, which is going to be the last one, okay? So the next homework is going to have implementation of sequential Monte Carlo methods, and I'm going to, it's already written, but I want to be sure that every sort of algorithm that you needed, it's somewhere inside the notes. So basically, you don't have to do lots of searching to locate the algorithm. So if something is missing, I'm going to be sure that in the next few days that I add the details in the slides. So today what I'm going to do is I'm going to tell you a little bit about using sequential important sampling and sampling for problems that they are not necessarily related to state space models, So not for dynamics, basically, but for any sort of problem. And in particular, I'm going to tell you how to use sequential Monte Carlo to sample from static problems with zero dynamics. Just here's the posterior, how do we sample from it? And I'm going to convince you that basically sequential Monte Carlo methods are the methods of choice for doing Monte Carlo these days. Of course, you know, this can mean 100 different things, except the fact that sequential means sequential. The rest are details that you will have to work out as you do one example or another. Okay, so I need to start. So I'm going to cover a few topics in some detail today, and the rest of the topics I'm going to superficially mention them and then move on from there. Okay, so we're going to talk about the general framework for, before we discuss the static problems, the general framework for using sequential Monte Carlo. And so here's the idea. Before we consider the state space model, all right, and we computed effectively an approximation to the posterior of the state x from 1 to n, given the data y 1 to n. So right now, I'm assuming there is no dynamics, there is no data, and I'm saying I have this posterior, all right, and I want somehow to do some Monte Carlo approximation of it. I only know the anormalized version of this distribution, and I want to do this in one piece after another. So I want to start with the distribution P1, then move to P2, to Pn, etc., where the space of all of these distributions, let's say the space of this distribution here is this calligraphic x to the power n. This is very important because when we discuss static problems, all of these distributions are going to be operating on this space x, not x to the n. But here the idea is I do have some sequential set of distributions, P1, P2, etc., and I want to sample from them, but there is no dynamics. So I cannot write equation about the dynamics. You remember when we had f of xn given xn minus 1, or we had an observation distribution, probability of y given x. I don't have any of that. So the idea here is I have a sequence, all right, and I'm going to see if it is possible for this sequence in general to apply this sequential importance sampling. Okay, so and of course we need, to do the same sort of calculations as before, calculate moments, expectations, normalization factors, etc. So let me, for this set of notes, to start with, is basically a review, but because there's no dynamics, the applicability is much more significant than what we saw a week ago. So the idea is we're going to start with some approximation of P1 and Z1, then we're going to proceed to Pi2, Z2, and it says here time 1, but keep in mind there is no really time. This is just the sequence of distributions the way they're given. So there's only one approximation or assumption that we need to have to make this methodology to work, and this approximation is that Pn of x from 1 to n minus 1, when is this positive, then Pn of minus 1 from x1 to n minus 1 has also to be positive. Pay attention in the notation, right? So this is my distribution at step n minus 1, and this is what? What is Pn with argument x1 to n minus 1? So this is my target distribution at step n minus 1, and this is what? I mean, my target distribution at step n is Pn of x from 1 to n. So what is this? This is the marginal, right? So you can appreciate the fact, right? We want some sort of this distribution to be very close to that distribution, okay? To make this to work, and in particularly when this is positive, we want this to be positive because most probably we're going to be using this to approximate the distribution Pn. Okay, the same way we did with dynamical problems. So let's start with time 1, and this is again a review of the notation. We're going to assume that we have an important sampling distribution Q1 of X1. So we take n samples from it. We create a Monte Carlo approximation of the distribution P1. This is an important sampling approximation. So you see the weights W1, and the weights in anormalized fashion is basically the anormalized target distribution pi of 1, which I call here gamma 1, divided by Q1. Okay? And the approximation of the normalization factor is basically 1 over n times the summation of all the little w's. Look at this and ask any questions, because this is sort of a review of the notation that we have seen in the last 2 lectures. So this is time 1. Samples come from a proposal distribution Q1. So the weights are gamma 1 over Q1. I don't need to know P1 exactly. I only need the normalized version of that. Using these weights and normalizing them, this is the normalized weights are capital W. I can write a Monte Carlo approximation of pi 1 that is given like that. All right? So let me put all of these things up. So the idea is when I move to time 2, I am going to have an important sampling distribution that is going to factorize the way that you see here. Again, no dynamics or anything like that. I'm going to create an importance distribution that is Q2 of X1 and X2, which is Q1 of X1 times some Q2 of X2 given X1. Okay? And of course, what we use here can make a big difference, but right now this is in general. So we sample X2. For each particle X1 that we sample on step 1, we sample X2 from here. And then I'm generating the weights. And I have given the weights, basically the total weights at time 2, but also the incremental weights that you see here. And look briefly through the derivation, because I want you to remember how this calculation came about. You remember the definition of the weights in important sampling is gamma 2 divided by Q2. This is the anormalized target distribution divided by the important sampling distribution. So this is gamma 2 again, like that. I approximate my Q to be like this. And then simply what I do is I multiply by gamma 1, and I bring Q1 on the first factor. So this is obviously my weight from time 1, and this is the incremental weight. Okay? And obviously the difficult thing here, and the whole aspect of the algorithm, is how do you compute this incremental weight? And of course here, I cannot assume any dynamics or anything. The only thing I know is the sequence of distributions, gamma 1, gamma 2, etc. And so this needs to be approximated in a very general sense. So this is how the algorithm looks in step n. This is how Q is going to factorize. Okay? So at step n, Qn is going to be xn given all the previous x's. So you can write this, you assume, let's say, at n minus 1 that you have all of the samples that are coming from this distribution, and then you, for each sample I, you sample from this Qn, all right, given x from 1 to n minus 1, and you get an xn. And the weights, again, look, the weights of the previous time step times the incremental weights. And so the normalized, so this is, if you want to normalize, you sum all of these things up. So you divide this by the summation, and you get this capital W. So this is the little w's, and this is the capital W's. Now, in the notes, almost everywhere in this set of notes, you're not going to see this factor here at all. So when I'm writing the weights at time n, you will only see this factor. So what's the implication there? So again, you're not going to see this thing appearing often. Because the idea is, what do we do to that factor? How do we get rid of it? I mean, it says there, actually. You remember that if you resample at each time step, right? What are the new weights you get with Monte Carlo for the approximation? 1 over? What do we do to get rid of this when we resample? So, you know, if I don't resample, right, my approximation will be summation over this capital W's, let's say, for each particle I, times this delta function at the location of each particle. If I resample, how is the approximation going to look? Instead of W's, what am I going to have instead? You see what a break does? It freezes your brain, and you don't remember these things, even though there is a homework here today. So what are the weights when you resample it? 1 over? Instead of W's, what are you going to have when you resample? When you do Monte Carlo sampling, no important sampling, what are the weights? 1 over n. So exactly, you will get 1 over n, right? So when you normalize these things, that doesn't come at all. So effectively, the weights, when you resample at this time step, this is the expression, this is exactly how they look like. So these are not the incremental weights, they're really the weights, okay? And since we have to resample to be sure we don't have degeneracy, we're going to assume, unless you see otherwise, it won't make any difference. Basically, these are the weights that we will consider from now on. So this is how the whole algorithm looks like, all right? And here you notice we sample to start with at step 1. We resample at step n, all right? So at every step we resample. So this is how the weights look like. Okay, these are the normalized weights. You know, and of course you want to keep track of this. Why? Because to resample, you need to know these weights. And where else do you need the W's? I mean, if I, you know, is there any other place where I need the W's in the whole algorithm that you don't see here? What do we need W to compute what? To compute the normalizing factor Z, exactly. So we need all the W's to calculate Z. Okay. So now there are no dynamics, right? So we have to do something about that factor. And you can show, right, that this optimal important sampling distribution of xn given all the previous x's is actually our target distribution at time n. This is a normalized gamma n of xn given x1 to n minus 1. Okay? So let's plug in this approximation in the general expression and pay attention to the notation here. So we don't really care about this. We will get rid of this. So I have 1 over gamma n minus 1, gamma n of xn, all right? And then I plug in gamma n of xn given x1, x from 1 to n minus 1. Can you tell me how I go from here to there? What have I used basically to go from this expression to that? I mean, I can see this factor on the denominator is that. So what have I done here to get that? Here I have gamma n, right, with arguments x1 to xn, and here I have the conditional of gamma n xn given all the previous arguments. So what do I get when I divide those two? You get gamma n of from x1 to n minus 1. And I remind you, this gamma n has integrated out argument xn. Don't get confused with the indices, right? Gamma n minus 1 takes n minus 1 arguments. So this is the whole target distribution. This is the target distribution time n, but xn has been integrated out. Okay? So look now at something very, so I wrote it here explicitly what gamma n x1 to n minus 1 is. So the incremental weights, basically, look at the ratio of gamma n divided by gamma n minus 1, and you notice something very interesting here. xn doesn't come in this picture at all. Okay, so this is an interesting fact, basically, using this optimal importance density. There is no xn coming at all in this picture. So what does that mean? It means that you can compute these weights using the previous samples by using this division here of the 2 gamma n and gamma n minus 1. And if this weight comes to be very small, then what do? You say don't ever calculate xn, start again from scratch. So in other words, there's no reason to build xn when this weight that defines the weights at time n is very small. So you don't need to compute first xn, compute the weight, and then say is it small, yes or no, because here this is independent of xn. Okay. So let me discuss, so this is very general, so let's discuss something I already mentioned in the general sequential important sampling lecture. So let's calculate the variance of the estimator, and in particular I'm going to concentrate in the variance of the approximation we do for the normalization factor Zn. The calculation is very informative, and it tells you why there is nothing is as rosy as it looks with equations. So do we agree that the estimator of Z at time n is given by this summation here? I mean, we proved this, okay? Is this, everybody agrees that the estimation of the normalization is 1 over n, the summation of the little w's? Yes? All right? So do you agree with me that the variance of this is 1 over n squared times, I have n terms, n times the variance of this for each particle? I mean, I should have put actually there, if you like, I should have put an I there, right? I forgot the summation here is on the particles, all right? But when I write it like that, since this is the same for all particles, what I have is 1 over n times the variance of the weight corresponding to any particle. Okay? And that's why I did not put an I there. So let's expand this, 1 over n. The variance of this is w squared. I'm taking the variance with respect to q, all right? So the expectation of w squared with respect to q minus the expectation of w squared, okay? This is gamma squared over q squared, so it's really gamma squared over q, one of the q's cancels. And this is gamma over q, the q cancels, so I have this gamma integrated out. Do you agree with me that this term is nothing else but Zn, the exact Zn, by definition, right? And so on the first term, I have, as I said, we have, well, I mean, you can, gamma, you can write it as pi times z, right? This is the anormalized version of pi. I put z outside. So basically there's a z squared there, a z squared there. This is the exact z. And here is what I can get. I can get that the relative variance of my estimator is 1 over n times this nice expression. Okay? This is very general. And this is something, you need to worry when you do, you program this for your research. This is a nice analytical expression. So what I'm going to do is I'm going to find you a case that demonstrates that we can get in trouble very easily. So here's the case. I am going to assume a very trivial case that this distribution Pn is nothing else but the end product of normal Gaussian distributions. Mean 0, variance 1. Okay? I mean, nothing exciting. But, you know, I can build a sequence. I start with one Gaussian, then n times n times n times n, right? So this is my target distribution step n. So the anormalized distribution is basically e to the minus x squared over 2, right, variance 1. And I'm going to take a proposal distribution that has a similar factorization over n, but I'm going to put some variance there, sigma squared. We have done this example actually in the easy setting when we talked about important sampling early on in the course. Okay? So I'm going to take a particular case where pi n is given by this, and the q's is given by that, and I'm going to plug in all of these things inside there. So if you plug them in, and I know you don't like algebra, but there is really nothing. It's simple. This is what you get at the end of the day. And you should do these calculations or look at it. There's nothing to do really. You look and you say, yep, I understand it. So the calculation comes that the relative variance is 1 over n, sigma to the 4th, divided by this, the power n over 2 minus 1. So guess now what I'm going to try to do to demonstrate that we can get in trouble. When you do calculations, right, when you write a computer code to do sequential important sampling, what do you like to see on this relative variance of your estimator? I mean, what's your objective when you do Monte Carlo approximation? What would you like to see? You want to be a small number, right? So you say, you know what, if this is 0.01, that's fantastic. You know, that's very good. Well, if this is 0.01, and let's say you have selected some sigma, then somebody can ask, what is the minimum number of the particles that I need for a given little n, so that this thing it is indeed 0.001. So let's see the calculation. If you want this to be 0.01, and you take sigma squared to be, it has to be greater than 1 for this argument to work. Obviously, we have done this before again. So you plug in this, and it comes that the number of particles that you need is 10 to the 8th. So, you know, I know I have people like Yin Hao asking me, is 10 samples good enough? You know, this is what everybody is using. Well, you know, you have to be careful because now you see, in a very simple setting here, with univariate Gaussians, the number of particles is 10 to the 8th. Okay? So, troubles ahead, basically. Okay? And the number of time steps is only, you know, did this for n equals 1,000, but even if you drop this down, you know, this number would still be a high number. So what do you think we need to do to resolve this problem? I forgot to mention, obviously, there is nothing actually to mention. When I did this derivation here, there is one thing I have not done on my important sampling approximations. What is that? This is sort of a vanilla important sampling approximation. What we said we have to do to avoid degeneracy, you know, as little n increases. We have to resample, all right? And if possible, if, you know, necessary, resample every time step. So if you actually resample, the variance of the estimator, okay, is given not by the expression that I had before, but by this very interesting looking expression that it takes about, you know, 2 pages to prove, and I give you a reference if you want to read about it, okay? So if you resample at each time step, this is what the asymptotic variance of the z looks like, okay? It's a little bit more complicated than before, okay? But it looks at this in this form. By the way, this is used a lot in this lecture, so you may want to just take a good look. So when you have to use it, you can put your own equations or whatever you need on the top of this equation. So I'm going to do the same approximations. My Pn will be the product of these n univariate Gaussians. So this is the gamma n. And I'm going to say make the same approximation for Q. And now what I need to do is I need to go and plug in things in here. And this is a little bit complicated because I see Pn squared over Pk minus 1. So it seems, you know, there's integration here on the arguments k minus 1 and k, and then a summation. So it looks messy. So here is a trick. Look on the equation on the top and tell me what is the trick that's being done here. I mean, I want basically to find the bound for the relative variance of my estimator when I resample. So what exactly am I doing in here? First, you know, how do we go from here to there? The integration, I see, remains the same. So what has happened here? Remember that in our case, right, we had this factorization. All right, so what you see on this slide incorporates that factorization. So I notice here there is a Pn, all right, Pn from x1 to k minus 1. From where did this thing come from? So if you notice, so tell me what's the difference of Pn from x1 to k, and all right, and then I have, let's see, Pk minus 1. Now you're going to have to help me too in case there's a typo there. I know there's no typo because I think I checked it. I did the calculation by hand 3 hours ago. So you guys have to tell me what's going on here. So I have on the numerator, right, I have two Pn's with argument x1 to k, okay? Remember, this is distribution Pn, the arguments x1 to xk. So I have one Pn and then another Pn, okay? In one of the Pn's with arguments x1 to k, I can write it as Pn of x1 to k minus 1, and then a conditional of the Pn of xk given all the arguments x1 to k minus 1. Can I do that? And on the other term that I have here, Pn of x1 to k and pk minus 1, x1 to k minus 1, let me see, Pn, this is there. Okay. In order to get Pn square of xk means all the other factors on this thing have to disappear. So where did they go? Remember that the distribution looks like that, right? So when I have Pn with arguments x1 to k, all the Gaussians from k plus 1 to n have disappeared because when I integrate them out, right, I get 1. Correct? So basically, one of these terms will cancel with the term of the denominator, and the only thing I'm going to get is Pn of xk, because they're all invariant Gaussians. Anyways, check the algebra, all right? I am doing a little trick on the second term, okay? And I am saying that this, so this is equal to that. There is no approximation. It is less or equal to this integral. From where is this coming? This is a probability distribution, so what have I assumed there? All right, and what? Notice here the integration is xk minus 1 and k, all right? So basically, if you do the integration on k minus 1, all right, actually, most probably the inequality, I don't remember now, maybe I messed it up, should go there. But anyways, there is no argument here, 1 to k minus 1. So when I integrate everything before k minus 1, they will give me normalization factor 1. And then I have Pn of x k minus 1, dx k minus 1. And this is less or equal to what you see here. So it comes out, you know, and I maybe make it to look that it's very complicated, all right? I don't think it is, actually, but it's hard for my brain to operate at this speed. So when you calculate basically this, it comes out that the relative variance, when you resample, is given by 1 over n times the summation, okay? So it's a little bit different than what we had before. So in this case, when you plug in all your distributions, what you get is little n divided by capital N, this to the power 1/2 minus 1. So when you put the same numbers as before, so you put the relative variance to be 0.01, you put sigma squared to be 1.2, n equal to 1,000, then what it comes out that you need only 1,500 samples versus 10 to the 8th, which is not bad. So basically, we went from a huge number of samples to reach this relative variance in the estimation of z to only 1,500 samples. Okay? So resampling pays off in this simple case. Of course, you know, in other complicated problems, maybe the reduction will not be as significant, but this tells you that resampling is essential. All right, so let me do rapidly one example on a very historical paper on sequential Monte Carlo that goes back in 1954, okay? And the title of this paper is Poor Man's Monte Carlo. By the way, this is one of your homework problems, so there is a reason to pay attention. And effectively what it is growing a polymer in a 2D lattice, okay? So let me describe this first with a picture maybe. I'm going to go. So effectively what I need to do is I have, let's say, 25 molecules, all right, that can be anywhere in this lattice space in a way that the molecules don't overlap with each other. So you cannot basically have two molecules on the top of each other. So you can see this is a path that I designed by starting at this point, then moving there, etc. And this is one of the many paths. So you can appreciate, and the calculation actually, I think it is part of your homework problem, that if you try to do this on a lattice that, I don't know, it's 10 by 10, for example, and you try to find what is all the numbers of all possible molecule realizations, of all possible chains of these molecules that you can have, the number is huge, all right? So what we need to do is, we need to find a way to sample from the distribution of these molecule paths. And why someone is interested to sample from the distribution of these molecule chains? Can you guess basically why this may be useful information, you know? And of course, this is a very simple case, right? But let's say, don't you think the actual length of this, the mean length of this chain, it may be important to physics? How do you calculate the mean length of the chain? Basically, you are going to need to have the distribution, and in the easiest case, take a Monte Carlo approximation from there to compute what is the average length of this chain when you have 25 molecules, all right? So we need to have a way to construct the underlying distribution from where these paths are coming. So this is a sequential Monte Carlo problem, and let me describe it in very simple terms, and then you can read the rest in the notes. So the idea here is the unnormalized distribution is given by the form that you see on the right, using the indicator function, where at time n, this domain AN is basically the lattice domain where there is no overlap between two molecules. You don't have to read everything. It basically says the xi and xj cannot coincide with each other, okay? So effectively, the idea here is I am going to approximate the distribution of all possible chains of P of x to be 1 over Z of n. So I'm going to take that all chains of, in this case, n plus 1 molecules are equal, of equal probability, but this distribution is very complicated because this normalization factor, it is very hard to compute. Can you remind me where the normalization factor was coming to be very important? Give me some problems. We discussed one, I remember one case that may come up in the lecture again today. Where did the normalization factor was coming to be very important? When we were modeling what? The probability of? Anybody remember? It was actually the expression, it was very similar sort of to what you see here, all right? But we were modeling the probability of failure, okay? So here, we're basically trying to model the distribution in a non-overlapping space, all right? So in many ways, the two problems mathematically have the same structure, okay? So we want to be able to sample, but this P of x is not useful because Z of n is difficult to compute. Now, do we know, let's say at each time, do we know what gamma of x is? The normalized version of P of x. Do we know what gamma of x is? How much it is? I mean, P of x is 1 over Z of n, the normalization factor. So what is gamma of x? It's equal to 1. So if we can construct some proposal distribution Q, we can do sequential importance sampling. So I'm going to give you, in simple terms, how we are going to construct that. So let me just, I'm going to try to find some equation somewhere. All right, so I'm going to construct as follows. Let's say, so we're going to try to introduce a proposal distribution Q that will allow us at each step to build basically a realization of this chain. So we're going to start at, let's say at some point 0, 0 in my lattice. So we're going to build the first segment where the next molecule is going to go. And the idea is we work in 2 dimensions. So the next molecule can be on the top, on the bottom, left and right. And any of these locations comes with equal probability, so the probability basically to be, let's say, there is 1/4. We can see that? Okay? So the segments here, we assume that the bonds basically, if you like, they're of length 1, so that these molecules coincide with lattice locations. So the probability of going from here to there is 1/4. Now, the probability of going from here to there, I claim is 1/3. Why is that? It cannot go back because we don't want overlapping 2 molecules, right? They don't supposed to be on the top of each other. Similarly, there 1/3, there's 1/3, that is equal to 1 over 108. Similarly here, you start 1/4, 1/3, 1/3, 1/3, you get something like that. But actually, you know what? You have to be very careful here, and that's why I gave it to you as a homework. You notice when I am at location 4 and I try to go to 5, how many different places can I go? So if I'm at 4 and I want to go to 5, how many different places I can go? I can go basically to 2, but the way that I have the probability here is 1/3 is the following. I say, well, I cannot go backwards because you have to move forwards always, but you can move to 1, which will not be good. You can move up, you can move to the left, probability 1/3. Now, if it happens that you move to point 1, then you basically have to destroy this chain and start again from scratch. This is how it was originally proposed, okay? But otherwise, the probability of moving from 4 to 5 is going to be basically 1/2, right? But here you see 1/3, right? And if it happens that the probability 1/3 you go back to 1, this will be rejected, and basically this will not be an acceptable sample, and you have to start from scratch. So let me give you the general formula. look, so you try to move from n minus 1 to location n, and I claim here that my proposal distribution is 1 over eta subscript n minus 1. So what do you think this is? This is the number of free locations that the molecule can move from n minus 1 to n. Okay? So if you put all of this together, the importance distribution basically looks like 1 over n1 and 2 and n minus 1. If you want the incremental weights at each time, the incremental weight is basically eta n minus 1. All right? From there, basically, you can compute anything you want to. And if you want to find a normalization factor, you can compute that as well. And that is part of your homework that you guys have to work out in about 2 weeks. Okay. All right, so let me move to a little bit more difficult topic now. So we need to discuss about using sequential importance sampling for static problems where there is not even a subscript n. In other words, somebody gives you a very high dimensional posterior and tells you sample from it. Okay? Can we use sequential importance sampling? So let's see how we can cook up the problem so that it looks as a dynamic problem where maybe sequential importance sampling can be used. Can I put an index n basically when I do calculation of posterior and my data are collected sequentially, y1 to n? So what, here it says sequential Bayesian inference. So basically what am I doing here to make the problem to look like a dynamic problem? The subscript basically n will denote what? I affiliate it not with time, but with what? So what is y? So the only place where n comes, right, explicitly, is in the collection of data, y1 to n. I have n data points. So when I put there in the posterior the subscript n, this is the posterior at the time at which I have collected how many data? N. So basically, isn't it Bayesian inference sequential in nature? There is immediately any problem of Bayesian estimation can be written using sequential Monte Carlo by using especially, in particular this notation that you see there. Okay? Now, notice in this problem, let's say that x is what you want to compute, right? All of these distributions Pn are of fixed dimension. This is a unique feature now. We did not have this before. You never before, at time 1 we had x1, then at time 2 we had x1 and x2, then at time 3 x1 and x2 and x3. But here all the distributions Pn have only one argument, which is x. It's a static problem. So yes, there is a subscript there, n, nice, but the estimation is static, doesn't change with that. It's the same variable. So before the space of this was, you remember calligraphic x to the power n? That's where the domain of the variables was belonging. But right now, the space of little x is fixed for all n. All right? And that's why I said, this is, if you want, there is no really n, p of x there, okay? Classical Bayesian inference without any n. You can use this to do global optimization that I haven't really discussed, like, like annealing sort of processes. And there, by introducing a temperature factor gamma n that goes to infinity, it's an increasing sequence, you can use this for optimization, basically, to find the mode, let's say, of the distribution p of x. But I want to concentrate on this problem here, which is usually the setup that most of you, if you work in this area, you will have to use to involve sequential Monte Carlo. So let me give you an interpretation, then you tell me what's going on. So we said we're going to make Pn of x to be the posteriors who collect data, all right? So let's say Pn of x is the posterior when I collected all my data points, all right? So the argument x is constant, okay? And let's say my prior is mu1 of x. So I want you to look in what it says here and tell me exactly what am I doing here. I'm constructing a sequence basically of distributions, all right, that converge to the actual posterior P of x, starting from where? From the prior until eventually I reach at some time this little n to be equal to 0, and then this becomes 1, and this becomes the actual target distribution P of x. The idea here is, right, you have the prior, you have the posterior, you built a sequence of distributions that gradually take you from the prior to the posterior, artificially, okay? So at time 1, this is equal to 1, this is 0, so I start with the prior, okay? And then, you know, you start basically reducing the sequence until you reach 0, and at 0 this is 1, and this is basically 1, which is your target distribution. So I want you to remember this example on where the static properties will be used. If you want to have any target distribution pi of x, you can create a sequence of distributions that slowly take you from an easy to sample distribution mu1 to the difficult to sample distribution P of x. Make sense? Can be anything, all right? So we create an artificial sequence, not dynamics or anything, but it's a sequence of distributions that take us from mu1 to pi of x. Now, this is very different from what I started the lecture today, because in the previous thing we had a sequence of distributions Pn of x, but the argument had n arguments. Here the argument of all of these distributions is fixed, is x. Understanding the problem here is, 99% of the solution, all right? So one is, we want to sample from P of x. We do this progressively by starting sampling from anything that's easy to sample, like a prior, and then gradually pushing this Pn of x to convert to the target distribution P of x. Okay? So effectively, the idea here is if you sample from mu1 with n1 to be equal to 1, those samples will be useful to calculate P2 of x. And those samples for P2 of x will be useful to calculate P3 of x, etc. But the difficulty here is that the argument of all the distributions Pn is constant. It doesn't change with n. Okay? So we need to deal with it. The other problem may be of interest to many of you, maybe again the calculation of rare events, okay? And I am giving you here the calculation, basically what the statement of the problem is, okay? So effectively, this, when you do rare event modeling, effectively you have to find the probability of some event A, and let's say this is your target estimator, or this is, the normalization factor basically is the probability of that event A. So what I do is, because it is very difficult to sample from A, I am sampling first, notice here, from events En, E1, E2, E3, etc., where En is subset of En minus 1. So these events become smaller and smaller and smaller, because a rare event is something that happens in that corner up there. So I start with a bigger domain, and I say, what's the probability that will be there? Then what is the probability of being a smaller domain, until I reach basically this domain P of A. So this it is very powerful because actually you can use this to calculate even things like volumes in high dimensions. Because you remember when you have high dimensions, where is most of the volume? It's in the edges. And you will never be able to sample directly from there, right? But with this idea of sequential importance sampling, you can start sampling in the bulk and then reducing this domain Cn until basically you reach the domain A and you reduce the samples and you're in business. Okay, how do we address these problems? This is the task we need to discuss in the next few minutes. Okay, so let me go to slide 46. Okay, the notation is going to start very similar to what we had before, but some weird things are going to come on the way. So we're going to start at time n plus n equal to 1 from some importance distribution, all right? So we come up with an importance sampling approximation of pi of 1, looks like that. This is the normalization factor. This is basically the how the weights look basically at step n minus 1, all right? And the idea is now we need somehow to move from n minus 1 to n, okay? And I am going to move using a transition kernel that is going to take me from x to x prime. And I want the stationary of that transition kernel Kn to be the distribution Qn from where I want to sample. So at n minus 1, right, we have a number of samples, all right? You can see how we can generate them at time 1. We can do anything we want to. So this is at time n minus 1, and these samples come from the distribution Qn minus 1. So now we need to be able to sample from the distribution Q subscript n. So what we're going to do is we're going to assume a transition kernel that has this as the target distribution. So Kn will take us from x to x prime. Okay? This is similar to what we had with an importance distribution that it was basically a Q of x prime given x, but I prefer to write this in terms of a forward transition kernel, and you will see shortly why. Okay, so let's see if we are going to need a transition kernel. This can be sort of a random walk or anything you want to. Let's see what how the calculation will look like. If you take this equation and you write it recursively, this is how Qn looks like. Qn is the product of Q1 times the product of all of these transition kernels integrated from x1 to n minus 1. So what this line basically tells you, and I'm not going to read it, right? Building a Qn with this way is not going to work. It's going to be extremely complicated, okay? You can think of this having to do a high-dimensional integration that will allow you to sample basically from Qn of xn, so this will not be very useful. You can do lots of tricks in between to alleviate, but somehow this will not work. Okay, major step. All of these distributions Pn have a fixed argument, so we need to somehow resolve this problem to build sequential Monte Carlo in the picture. So we're going to operate in an augmented space, not the space of little x, but in an augmented space that increases with n. And how can I do this? We can do this by defining a new sequence of distributions, this curly p curly subscript n, where it has my target distribution at time n, and then it has this conditional distribution that can be anything. You remember the problem was that all of our distributions, right, have a fixed argument, one argument only, okay? To do sequential Monte Carlo, we need to have, let's say at step n, we need to have arguments x1 to xn. So what I'm going to do is I'm going to create a new sequence of distributions in an augmented space. So here I have n arguments, where this new sequence of distributions has my target distribution times this conditional, and this conditional in principle can be anything you want to. I'm going to specify what that means, anything you want to, but basically this is sort of the trick that we need to introduce that will allow us to operate in the classical way sequential Monte Carlo operates. We're going to have to build this distribution, all right? Put something here that is going to be useful for us, but really our target is this fixed argument, basically distribution Pn of xn. So I'm going to explain with a very simple setup in at step 1 and step 2. So let's say that so we start at time 1, and we have, if I go back, right, I mentioned that at time 1, where was it? So at time 1, you can sample x1 from q1, and there is an important sampling distribution. So not an issue, right? So time 1, we're done. So let's do the following. Let's concentrate at time 2. What can we do at time 2? And, somebody will say, okay, to do important sampling at time 2, my target distribution is P2 of x2 divided by my important sampling, so this is the weight, Q2 of x2. And you notice there is only one argument there, x2. There is no x1 and x2. At time 2, I only have one argument. At time 3, I only have one argument. So this is the sample x2 at time 2, and this is the weight at time 2. So this cannot be evaluated, all right? But look at a trick. Let's say that I augment this, instead of having P2 of x2, to some new distribution that is P2 of x1 and x2. And you say, what is this distribution P2 of x1 and x2? Well, I am writing this as P2 of x2 times an arbitrary, look at this, backward Markov kernel that takes me from x2 to x1. So basically, rather than defining weights using my static variable x2, now I have the variables 1 and 2, x1 and x2, to represent the classical way we do sequential Monte Carlo, but there is no distribution P2 of x1 and x2. So I define one that is my target distribution P2 of x2 times a backward kernel that takes me from x2 to x1. And you may say, well, what's a backward kernel? Is anything that given x2 will give you x1? And let me explain why this will be actually a correct thing to do. Because look what happens. If I take this and integrate x1 out, so P2 of x2 will come outside, and then I have the integral of this backward kernel in x1. How much is that? If you have by definition a kernel that from x2 it takes you to x1, where x1 can be anything, and I integrate in x1, what's that integral? 1, regardless of what L1 is. So basically, by enhancing the space and adding L1, I have not really damaged anything. This is still, I'm on target. Okay? So the x1 here comes because I know how to deal with sequential important sampling with a distribution P2 of x1 and x2, but I have no idea how to deal with P2 of x2, P3 of x3, P4 of x4, etc. But now I have this sequential augmentation of the space, right? And this thing will take me to my target distribution because you can see here the derivation is going to look just right. So L1 is a backward kernel that takes me from x2 to x1. And notice now in the denominator where I have the important sampling distribution Q2 of x1 and x2, I already had Q1 of x1, and now I have a forward kernel that from x1 takes me to x2. The idea is I already sampled from x1 from Q1, now I need to sample x2, and I sample this with a forward kernel, K2 of x1 and x2. So this is a forward kernel, this is a backward kernel. Okay? So here is how the whole idea looks like. you define a target distribution in an augmented space where you go from a static argument x to an argument x1, x2, xn at time n, all right, where the unnormalized distribution at time n is my target distribution of only one argument, which is the one that I care, times the product of this backward kernels L that take me from k plus 1 to k. You understand basically the idea here is, right, bring these variables in the picture so I get n variables here even though my target is only this, okay? Why do I do this? Simply because I know how to do important sampling on dynamic problems having n arguments. I don't know how to do it with static arguments, okay? So these are the backward transitions, okay? So you can think of this, for example, how do you build, let's say, arguments on x1, x2, up to xn minus 1? Since you have a sample xn, with this, for every xn, you can go to x minus 1. Then with the next kernel, you can go from n minus 1 to n minus 2 until you hit basically x1. And I do the same thing with forward kernels, which is basically the way we did this anyways before, okay? So before, this is the notation we used, okay? This is our important sampling distribution, but right now, to maintain some consistency with these backward kernels, I use a forward kernels that take me from xk minus 1 to xk, okay? And again, the proof of validity is here. If you integrate all the arguments up to n minus 1 out, nothing is lost and you get exactly what you're interested in. So here is the final answer. If you try to do important sampling the way we do with sequential Monte Carlo, you build the ratio of gamma divided by q for all the arguments. You have your previous weights, okay? And you substitute now these gamma distributions, and eventually, because a lot of these transition kernels cancel out from this expression, this is what you get. You get an incremental weight, which is the target distribution. This is the actual target distribution, gamma n of xn and gamma n minus 1 of xn minus 1. And then you have a backward kernel that takes you from xn to xn minus 1, and a forward kernel that takes you from n minus 1 to n. By the way, this looks a little bit weird, but if you look at it visually, is there anything in sampling methods that this sort of reminds you at all? Where you had an unsymmetric term. They were not basically L and K, but there was something that was taking you forward and something that was taking you backwards. Anything in sampling methods that we have seen up to now that has basically, the target distribution sort of, pi or whatever we were using times the ratio of two other things there. Actually, I can tell you the ratio was the ratio of q's. There were the ratio of the important sampling distributions. Where was that thing coming in? Say it again? In the Metropolis-Hastings algorithm, the acceptance ratio, exactly. So in essence, this is not weird. This is exactly what Metropolis-Hastings was doing in defining the acceptance probability. Okay? So this is very general, all right? We enhance the space from xn to incorporate everything else. And you notice basically when you get the weights, a lot of things have canceled out because of this decomposition in the kernels. And here is the algorithm. All right? Is there any algorithm? Yes, here's the algorithm. So we start at time n, all right? We assume we already have samples at, at n minus 1. So this is sample I. We need to sample now xn. So we sample those from this transition forward kernel, kn, xn minus 1, xn. So we built, basically this is now our new samples at n minus 1 and n. We construct the incremental weights from the previous expression, and then our target distribution. And remember, our target distribution, we are only interested in the argument xn. The rest, you can get rid of them because you don't care about them. And this is the approximation for the target distribution. Okay? So, and of course, if you go and do resample, you get your classical Monte Carlo estimator that looks in the way you have this in the bottom. All right, so the task now is, what do you use for L? For K, you can, already you discussed, you can use random walks, Metropolis Hastings steps. You can actually use Gibbs sampling to approximate this, sort of conditional distributions. What do you use for backward kernels? That takes you from, this case, from xn minus 1 to xn. So let me see if I can go directly and give you the optimal, since we have limited time. So, yes, actually, slide 54, let's see. I'm going to go to slide 56, and then I'm going to come back to 55. So I'm going to give you the optimal thing you can do, okay? So the optimal backward kernel from xn to xn minus 1 is given basically by the importance sampling distribution at n minus 1 times this forward kernel from n minus 1 to n divided by the importance sampling distribution at xn. But the way you look at this and tell me if it reminds you anything. Look at this equation. This times that equals this times that. What's the buzzword there? Does this remind you anything, just like from all the words we have used when we talk about invariant distributions, So what does this remind you? Say it again. Detailed balance equation, or basically reversibility. Because this tells you sample xn from this, and then transition to xn minus 1, and then says, well, sample xn minus 1 from this, and then transition to xn, and you want to make the two things equal. Okay? And by the way, you can prove that this is the optimal. Okay? All right? And effectively, if you use this, things are simplified. Now, if you cannot calculate this exactly, any sort of approximations to this optimal backward kernel will do the job. If since we discuss about estimators for the static problems, I told you we're going to go back to slide 55. Somebody may say, and how do I approximate the normalization factor now from this type of calculations? Well, if you do the algebra, and there is a little bit of, nothing major. I put some color here to see from where the derivation comes. But effectively, if you want to find an approximation of the ratio of Zn over Zn minus 1, it's basically an importance sampling approximation where it is the previous weights, or if those are 1, times this incremental weights that we saw in the previous slide. Okay? You can do lots of fancy things. If you want, you can actually assume that both the forward kernels are summation of many kernels, or even a convolution of kernels. You can assume the backward kernels are summation of backward kernels. So you can try different type of approximations here. Nothing is being affected. Basically, the incremental importance weights have only to be changed by the coefficients alpha and beta. So the algebra is sort of straightforward from that. You can actually prove, and there is a book on the front, that you can come up with central limit type of approximations for this applications of sequential Monte Carlo static problems. The algebra, the equations are identical basically to what we have seen in earlier lectures, right? We actually saw a little bit of this earlier today, except those factors that we had here that involve the backwards and the forward kernels. Okay. Apart from that, the equations are identical. You can even compute the bias of these approximations, and I'm going to give you a suboptimal, so I can finish today, a suboptimal approximation of this backward kernel, where instead of using Q, you actually use Pn of xn minus 1 and Pn of xn. Okay? So if you use the suboptimal L, the incremental weights come to be the ratio of gamma n divided by gamma n minus 1 computed at the particles that you sample at time n minus 1. Okay? And in physics, this is something that they were already doing this without any mathematical proofs for almost 40 years, and it goes under the name of annealed important sampling. Okay? I mean, simulated annealing is very much related with this artificial building of sequences where temperature is used instead in physics. But this particular algorithm using this backward kernel was already known in physics for many years, and it was discovered basically in a tracking problem 10, 15 years ago. Okay, I don't have time. I'm going to maybe come back. You may want to ask the following. If you